Good morning. Once again, a warm welcome to online learning of chemistry. Last time, we have started halogen derivatives of alkanes. And we have studying halogen derivatives of alkanes, where we studied halogen derivatives of alkanes in three lectures, I would say. And we had stopped with chiral and achiral topic. Today, we are going to continue with the same topic of isomerism. Now we will study what do you mean by different rotations of these organic compounds. If you go to see, there are two types of rotations. One is clockwise and one is anti-clockwise. If you look at the screen, the first is dextro-rotatory compounds. What are dextro-rotatory compounds? My dear children, first study one, and opposite of this, you will study the second, that is levorotatory. So let us study what is dextro-rotatory compounds. The compounds which rotate the plane of plane polarized light towards right-hand side, that is clockwise. That is clockwise means how the arms of the clock rotates is called dextro-rotatory compounds. Now this is symbolically represented by a small d or a positive sign. So dextro-rotatory compounds are nothing but a compound which rotates the plane of plane polarized light towards right-hand side, that is clockwise, or I would say dextro-rotatory, or I would say small d, or I would say positive. This is dextro-rotatory compounds. The next rotation is levorotatory compounds. The compound which rotates the plane of plane polarized light towards the anti-clockwise, that is left-hand side, is called levorotatory compounds. That means it could be anti-clockwise, means against the rotation of arms of a clock. So it is represented by a symbol L. L small means levorotatory, and negative sign means it is anti-clockwise. So the difference between dextro-rotatory and levorotatory is dextro is right-hand side, clockwise, dextro-rotatory compounds, small d, positive signs. Levorotatory means left-hand side, anti-clockwise, small l, negative side. This is levorotatory compound. Now if you see in this two examples which are on the screen, that is lactic acid and 2-chlorobutane. If you see it, this is dextrorotatory lactic acid, where carboxylic group in both the cases is on the same side. CH3 methyl is on the same side, but here hydroxyl and hydroxyl, so they are mirror images of one another. If you see in 2-chlorobutane also, here it is ethyl group, here it is methyl group, which is in a mirror image with this L, 2-chlorobutane. This is clockwise, that is chlorine and chlorine. So here carbon atom is connected to 4 different groups. Here also if you see in lactic acid, so you can study in detail the properties of these two compounds, that is lactic acid and 2-chlorobutane. So we can study the optical activity of these compounds also. So here these are two mirror images, one is of lactic acid, D and L, and 2-chlorobutane, that is D and L. So one is dextro and one is levo. So if you see, concentrate on these two carbon atoms, where this carbon atom is connected by 4 different groups. One is ethyl, one is hydrogen, One is chlorine and one is methyl. Similarly, this is their mirror images. But if you try to lift this up and try to impose on this carbon atom, they are non-superimposable mirror images. What will coincide? Ethyl will coincide only, where methyl will be not coinciding. Chlorine also will not coincide with this chlorine, and this hydrogen will also not coincide with this hydrogen. So they are non-superimposable mirror images where we are having, and that's why these are known. Now, if you see here, this carbon atom is asymmetric carbon atom. Last time I have explained you what is asymmetric carbon atom. A carbon atom which is attached or bonded by 4 different groups is called as asymmetric. Now, this asymmetric carbon atom of 2-chlorobutane, if you try to impose on this, it is non-superimposable mirror images. Now, there is a property known as enantiomers. Now, what are these enantiomers? We have seen in the earlier slide the example of 2-chlorobutane. And we have seen that only one, that is ethyl, is coinciding with another when you try to superimpose. But they are non-superimposable mirror images. So enantiomer is something like that, that is optical isomers which are non-superimposable mirror images of each other, which rotate the plane of plane polarized light in the same direction, or not in the same direction, but the same angle, but opposite in direction. Very important here. The optical isomerism, which is non-superimposable mirror images to each other, which rotate the plane of plane polarized light in the same angle, but in opposite direction, are known as enantiomers or enantiomorphs or optical antipodes. If you go to the previous slide and see, concentrate on this. Now, if I try to, these are mirror images, they are non-superimposable mirror images, and they have an angle, they rotate, but they rotate in opposite direction. If I want to see dextro has a positive sign, so it rotates on the clockwise, so it will try to rotate in this direction. And whereas levo is anti-clockwise, so it will try to rotate in it. So they are opposite in direction, but at the same angle. If this is rotating by 30 degrees minus, it will also rotate 30 degrees plus. So this is very important. So rotation is there, definitely, but they are in opposite in direction. So in the same angle, 30 degrees, 45 degrees, or 60 degrees, whatever angle is there, but it is opposite. So they are known as enantiomers. So 2-chlorobutane and lactic acid are a very good example of these enantiomers. Now these enantiomers, they have identical physical properties like melting point. If you see why they should have identical, because nothing is changed, only the angle, only the direction is changed, that is opposite, positive and negative. But all their substituents are same. So they are having the same properties, that is melting point, physical boiling point, densities, refractive index, except the sign of optical rotation. So they have same chemical properties except towards optically active pHs. That is a very important topic in enantiomers, and which we should really concentrate, because this topic tells you the rotation, which tells you the angle, and which tells you the asymmetric carbon atom. The next is racemic mixture. What is racemic mixture? The equimolar mixture of enantiomers. These enantiomers. What are enantiomers? Non-superimposable mirror images of each other, which rotates the plane of plane polarized light either in opposite direction. It's not either in opposite direction, but in the same angle, but opposite in direction. Now this equimolar mixture of enantiomers, that is DNL. So DNL of chlorobutane, 2-chlorobutane or lactic acid, compounds which is optically inactive due to external composition is called as racemic mixture, or also called as racemates. So racemic, we always say racemic mixture. Now we are going to study one example, one reaction mechanism where we will get these products as racemic mixtures. They will get in 50% inversion in configuration, 50% retention in the configuration. And that time you'll be able to understand this concept very, very nicely. So racemate mixtures or racemates, it is designated as D or L. That is positive sign or negative sign. Before going to any studies earlier or further, there is certain things which are needed to be understood very, very carefully. Now, these are the two representations. One is a Fisher projection formula and one is a wedge formula. Now, what do you mean by Fisher projection formula? If you see here, now this is a central carbon atom, which I have said it is a chiral carbon atom. Why this is known as chiral carbon atom? Because this carbon atom having a valency of 4, it is bonded by chlorine, bromine, hydrogen and iodine. That is by 4 different atoms. And that's why I say this is a chiral carbon atom which is bonded by 4 different, and that's why I would also say it is an asymmetric carbon atom, and which is a Fisher projection. Now this, if you come to the next, that is a carbon atom, same structure, but it is represented in a different fashion. Now if you see here, this is known as a wedge line. A dark line is known as a wedge line. So there are 2 wedge lines here. This wedge line denotes you, these 2 substituents are above the plane of a paper, above the plane of it, which is very close to us. If you see here, the next is 2 dotted lines. One is chlorine and one is hydrogen. These 2 substituents are below the plane of a paper. So they are gone far away, and that's why anything far which we are not able to see very clearly is represented by a dotted line. So these are conventions of vertical and horizontal lines. If you come into the wedge formula, here there is a asymmetric carbon atom again, where it has got iodine, hydrogen, chlorine and bromine. Again, 4 different substituents which is there. Now these 2 substituents, that is bromine and chlorine, are in the plane of a paper, where this hydrogen is above the plane and iodine is below the plane. So this is the 2 representation which we should know very well when you are studying, especially stereochemistry. The next topic which we are going to cover today is we are trying to cover the chemical properties of haloalkanes. Haloalkanes can undergo different chemical properties. One is it can undergo nucleophilic substitution reaction. Then it can also some substitution reaction in advance. Elimination reactions are also there. And addition reaction is also there. So 3 types of reactions it can undergo. We are going to study the first, that is laboratory test for haloalkanes. Now we very well know what are haloalkanes. Haloalkanes are nothing but alkane substituted by a halogen, where one of the hydrogen of an alkane is being substituted by a halogen. And that's why we write haloalkanes in a general formula as Rx, where R is an alkyl group and X is a halogen. So when you warm this haloalkane with an aqueous alkali, alkali can be of any type, or sodium hydroxide or potassium hydroxide, this halogen atom is converted to a halide ion, How it is converted, see here, Rx, when we have taken this a hydroxyl group and an alkali, that is OH minus, it's a nucleophile. So this nucleophile will try to substitute this halogen, which may be chlorine, bromine and iodine, which is again a nucleophile. So I would say OH minus is a stronger nucleophile than X. So it is trying to substitute this nucleophile X, and that's why we get ROH. So from an alkyl halide, we get an alcohol, where X is a nucleophile, that is a halide ion. So when this reaction mixture is acidified by adding dilute nitric acid and silver nitrate, solution is added a precipitate of silver halide, which is here. So silver and a halide, that is the nucleophile, is added, is formed, which confirms the presence of halogen in the original organic compound, that is alkaline. So here silver is taken X-phase, silver metal I would say, is treated with this halide ion and you get silver hydride in the form of a precipitate. So this is the proof that there is a presence of halogen in the original organic compound, that is an alkyl halide, also called as haloalkanes. The second one is nucleophilic substitution reaction of haloalkanes. Nucleophilic, I said to you earlier that this nucleophile could be OH minus. And here, this is an alkyl halide, where this is a carbon to which some substitute is there, maybe hydrogen. Consider this is a hydrogen. So this is methyl halide. So there is a delta positive charge, inductive effect, if you see here, delta positive charge, and a delta negative sign. So in alkyl halide, CH bond is a polar bond because this carbon acquires a delta positive charge and a halogen acquires a delta negative charge. And hence, this carbon to halogen, carbon is electrophilic center. Therefore, there is a tendency to react with this nucleophile that is here. And that's why this bond has been broken and a new bond is formed between carbon and nucleophile. And this halide nucleophile is there. So the reactivity of alkyl halide depends upon the substrate state and the nature of the halogen atom. Now halogen atom, when I say nature of the halogen, chlorine, bromine, iodine, chlorine, and so on. So the order of the reactivity of this halogen atom is the Ri, nature of the halogen atom is RMS iodide, greater than alkyl bromide, greater than alkyl chloride. Chlorine is the most electronegative, and that's why we did not, most of the time we take only bromine and chlorine in this reaction. Iodine also is very electropositive, and that's why we don't do iodine as a halogen. Coming to the very important aspect, that is chemical properties of haloalkanes. Now these are some important nucleophilic substitution reactions which we are going to study. In the earlier reaction, we have studied what is alkyl halide, and we have treated an alkyl halide with NaOH. Now here this is formation of alcohols. Now here we are taking as a starting product as alkyl halide as one of the reactants, trying to react this alkyl halide Rx with sodium hydroxide, aqueous. So aqueous alkali I would say, maybe NaOH or KOH, heat it. You get a substitution reaction taking place where this R ionizes are R plus and X minus, where this alkali also ionizes Na plus and OH minus. So these X and OH minus, both are nucleophile. But as I said earlier, OH minus is a stronger nucleophile than X minus. And as such, this OH is getting substituted, this OH is substituting X, and that's why we get an alcohol that is ROH, and NaH, sodium halide is formed. So either you can get sodium halide or potassium halide. So by this you can get alcohols from alkyl halides. So in this case, I can take ethyl bromide as an example, treat with either NaOH or KOH. Definitely this has to be aqueous alkali, NaOH or KOH. Heat it, you will get ethyl alcohol, and either if you are using sodium, you will get sodium bromide. If you are using potassium, you will get potassium bromide. So this is one method to prepare alcohol. So this becomes the method of preparation of alcohols when you are studying an alcohol topic. We'll again discuss this method. But here it is a chemical property of haloalkanes or alkyl halides. The second chemical property is formation of ether by Williamson's synthesis. Now Williamson was a scientist who derived the synthesis to prepare ether. Again, it becomes the method of preparation of ether. So when we are studying the topic, we will again discuss this reaction. But here it is reaction of alkyl halides. So we have taken an alkyl halide and treated this alkyl halide in presence of sodium alkoxide. Now this is sodium alkoxide, that is NaO and R. So here R can be any alkyl group. Here also R can be any alkyl group. So here you have to ionize this Rx, R plus and X minus. Here you have to ionize this sodium alkoxide as NaO, that is Na plus and OR minus. Here I've used R and R dash to clearly identify which is this R, whether this R is of alkyl halide, where this R dash is of alkoxide. So here there is a simple reaction taking place where R, O, R are getting connected, and you are getting here that is R, O, R dash. So this O and R dash are from alkoxide, and this R is from alkyl halide. So you're getting an ether, and sodium and halogen are forming sodium halide. So here, if you see here this example, that is ethyl chloride, that is here it is an R, CH3, CH2 is R, and Cl is an halogen. So I am treated with sodium, that is sodium ethoxide. So here there will be ionization here. Na and Cl will form. So this will form NaCl, where you will get CH3, CH2O, CH3. So you will get a mixed ether, that is ethyl methyl ether. It's a mixed ether. So you can prepare your ethers by this. But this is the chemical property of an alkyl halide, where we can prepare from alkyl halide ethers. The third reaction in this topic is formation of esters. Now we very well know what are esters. We have studied in the 11th standard different functional groups. So what is esters? So if you go to see what is ester, it is nothing but there is a ester linkage. Now this formation of esters is from silver salt of carboxylic acid. Now when we say silver salt of carboxylic acid, we'll study here, we'll see here, this is R, C double bond O, OH. So if you see the carboxylic acid general formula is RCOOH. So one of the hydrogen is been substituted by silver, and that's why we call it as silver salt of an carboxylic acid. Now here it is an alkyl halide. So alkyl halide is Rx, so R plus X minus. Where in silver salt of carboxylic acid, this is silver carboxylate, where silver is positive, Ag is positive. So O, C double bond O, R. That means RCOO minus. So this is an ion of an acid. So here there is an exchange where silver and halogen will form AgCl, which is the forming a precipitate, and that's why there is a down arrow. And here you are getting a formation of ester. Here ester is formed, that is RC double bond OOR. Now this R is coming from a halide, that is alkyl halide. So it's coming from it, where this R dash is of a silver carboxylate. If you see in the example, we have methyl bromide. Now this methyl bromide is treated with silver acetate. The silver acetate is CH3, C double bond O, that is COO, Ag, where Ag, I said, is from Ag is substituting hydrogen of an acid, and that's why it is silver acetate. Is heated, you get CH3, COO, that is this part is here, and to this part CH3 has been attached, and AgBr is formed, that is silver bromide, and here you get methyl acetate, methyl acid. Now this is a methyl and this is an acetate linkage, and it is also known as methyl ethionate. Now why methyl ethionate? This is methyl, and this is ester. Any ester is known as 8, ATE. And since there are 2 carbon atoms here, if you see here, there are 2 carbon, and that's why the word came ethane. And since there is a ether linkage, ester linkage, and that's why it is called as ethionate. So here this is a methyl, this is the ester linkage, and that's why, see, there are 2 carbon atoms, and that's why it is called as methyl ethionate. So this is nothing but a ester. So you can also prepare esters from alkyl halides. The next reaction is formation of amines. Now this formation of amines is only particularly with primary amine, where we are getting NH2 linkage. Now here alkyl halide. Alkyl halide is treated with alcoholic ammonia NH3 in excess. There is also heating and also there is a pressure because a lot of high temperature is required. The reaction condition needs to be very high, and that's why to avoid the reaction condition, there is also a pressure. Vacuum we say, under vacuum, under pressure, different terms are used. So here you are taking an alkyl halide or haloalkane treated with alcoholic ammonia. And here you are getting one of the hydrogen of this ammonia is linked with X, is getting connected with X. So here you get RNH2, which is a primary amine. NH2 means primary amine. NH means secondary amine. And N means tertiary amine. So here it is primary amine, that is RNH2. And here you are getting hydrogen halide. Here one example is there, ethyl bromide treated with alcoholic ammonia heated under pressure gives you ethylamine, that is CH3CH2. Here one of the hydrogen is getting linked or forming hydrogen bromide, and that's why you get HBr, and one hydrogen is less, so that becomes NH3 becomes NH2, and that's why you get ethylamine, which is a primary amine. So these are the four methods of preparation which you have studied up till now. We'll go to the next. Fifth, that is formation of alkyl cyanides. Now these alkyl cyanides are also known as alkyl nitriles. These are also known as alkyl nitriles. Now what is any cyanide? Any cyanide is poisonous. Any cyanide is poisonous. Any cyanide which is there in the environment, in the laboratory is kept very careful. Now here, before you were born, there was a major accident which had taken place in 1982. And that was Bhopal gas tragedy. And at that time, methyl isocyanate was a gas leakage in Bhopal, and many people suffered. There was a massive accident there. So that is, any cyanide is poisonous. The moment it comes in contact with your blood, the precipitation of the blood takes place. In simple language, and a person dies because there is no circulation of the blood. And it's very dangerous. So formation of alkyl cyanide. We are going to prepare cyanide only on paper, not in the laboratory. And when you're preparing in the laboratory, it is prepared under lot of precautions. When you go to the postgraduate classes, definitely one preparation is there, which I do not know. When we were students, when I was a student, we had to deal with the cyanide. And our teacher that time had told us to be very careful. There should be no cuts on your body. You have to follow all precautions of mask and everything, of hand gloves and the kit and the shoes, everything. But now we'll prepare it on the paper. Now here, when alkyl halide, like methyl iodide, is treated with potassium cyanide, KCl, alcoholic potassium cyanide, heat it, you get formation of RCN, that is alkyl cyanide, also known as alkyl nitriles, which here when you take methyl iodide, treat with KCl alcoholic, you will get methyl cyanide, which is methyl cyanide, also known as ethane nitrile. Why ethane nitrile again? Here there are two carbon atoms, and this is nitrogen here. And that's why it is known as ethane nitrile, and potassium iodide is a byproduct. So here, when you are doing this reaction, when you do your research and all, you see that you are very careful with any type of cyanides. It is dangerous for your health. Now your formation of isocyanide. Now isocyanide and cyanide both are dangerous. Now here, alkyl halide is there. Alkyl halide treated with AgCN. AgCN is silver cyanide. Alcoholic again, heat, you get isocyanide formation. Now what is different by cyanide and isocyanide? Cyanide is CN, but isocyanide is NC. Only difference is how to remember cyanide. Cyanide is CN, and here isocyanide is NC. Here you get a silver halide precipitate. So you take methyl bromide as an alkyl halide, treat with it AgCN, alcoholic, heat it, you will get CH3NC plus silver bromide, methyl isocyanate. So here it is abundant nucleophile. This is an abundant nucleophile. Here, very capable of attacking through more than one site at a time. So very you have to be very careful with this both the type of reactions, that is cyanides and isocyanates. We'll go to the next reaction of alkyl halide. It is formation of alkyl nitriles. Alkyl nitriles. Now, what are these alkyl nitriles? Here, as usual, there is a RX, that is methyl bromide. It's an alkyl halide treated with potassium nitrite. This potassium nitrite is KNO2. KNO2, potassium nitrite. KNO2. So this is a potassium nitrite, and you get the alkyl nitrile, which is CH3ONOO. So you get a methyl nitrate and a byproduct. So all this reaction which we have studied now is substitution reaction. Next is formation of nitroalkane. Nitroalkane. Here you take alkyl halide, that is CH3, CH2. This is ethyl chloride, and you get a silver nitrite, that is AgNO2, silver nitrite. You take ethyl, you get a reaction that X is being substituted, and you get silver halide, that is silver chloride. Here in the silver halide precipitated form, and you get ethyl, that is nitroethane. So you get RNO2, that is the nitro group. So you get ethyl, that is nitroethane. So nitroethane is a product. Now, we have studied all types of substitution reactions. So first, what we studied, we just roughly, hurriedly brush up. First, we have seen we can prepare alcohols from alkyl halides. Second, we saw preparation of ether from alkyl halides by Williamson synthesis. Third, we saw we can prepare esters from alkyl halides using silver salt of carboxylic acids. Then we saw the preparation of primary amines from alkyl halides by using alcoholic ammonia. Then we said we can prepare cyanides, that is alkyl cyanides from alkyl halides using alcoholic potassium cyanide. We said we can also prepare methyl isocyanate or isocyanate compounds from using alkyl halides using alcoholic silver cyanide. And then we said we can prepare nitriles from using alkyl halides by treating alkyl halides with potassium nitriles, and you get the alkyl nitrites. And also we said we can prepare nitroalkanes from alkyl halides using silver nitrides from alkyl nitroalkanes. So these are the different methods of preparation of, these are the different chemical properties of alkyl halides. Next is what we are going to study in detail is mechanism. Now what is SN? S means substitution, N stands for nucleophilic. The mechanism of SN reaction. Now we have studied earlier in the same lecture, I have explained you this reaction. This is a carbon atom. A carbon atom which is having delta negative charge, a delta positive charge, and a halogen which is having a delta negative charge. So partially positive and partially negative. So this is the bond between carbon and halogen which is to be broken, and this X will be substituted by a new nucleophile which is shown here, and X is again a nucleophile which is negatively charged. Now the substrate undergoes two changes. First, the original CX bond undergoes heterolysis. Heterolysis means two different charges, delta positive and delta negative. Then a new bond is formed between a carbon and a nucleophile. So there is a breaking of this bond and a formation of bond. So there are the two things which we should know very well. Whenever there has to be a reaction taking place, there has to be a reactant. So this is one reactant, this is another reactant, and then only there is a reactant. When there are two reactants, there is a reaction taking place, and then you get a product and a byproduct. So here, if I take here, say CS3X, CS3Cl, and I treat this with NaOH, so I'll get here CS3OH and HCl. So I get a main product, an alcohol, and I get a byproduct, that is HCl. So here mechanism of SN, that is substitution nucleophilic reaction, means the description regarding the sequence and the way in which the two changes takes place. How is the reaction taking place? Very important. It may be one or more steps reaction mechanism. So there are two mechanisms observed in SN reaction. SN means, I told you, substitution nucleophilic reaction. So there are two mechanisms, whereas one is SN1. S stands for substitution, N stands for nucleophilic, 1 stands for unimolecular. Only one molecule is responsible for the rate of the reaction. And that's why it is known as SN1 reaction mechanism. SN2 means substitution, nucleophilic, biomolecular. So SN1 is also denoted as SN dash, 1 dash only. And SN2 is also denoted as SN double dash. So substitution, nucleophilic, unimolecular reaction mechanism, substitution, nucleophilic, biomolecular reaction mechanism. So these are the mechanisms which is there, which has to be understood. Now, because of lack of time, we will stop this lecture here, and we will try to meet sometime later. Prior to that, I will just show you one more thing which is there. SN2 reaction mechanism. SN2 means what? It is substitution, nucleophilic, biomolecular. Here when you are taking SN2 reaction mechanism, or when you are studying SN2 reaction mechanism, what is the reactant which you are going to take? Very important is methyl bromide. What is the structure? C, and there are 3 hydrogens, one here, and there is a bond between carbon and bromine. So this is the bond carbon and bromine which has to be broken, partially formed, and a new bond is formed between carbon and hydroxyl. So I take this methyl bromide and I take a nucleophile, OH minus. This OH minus comes from either with sodium hydroxide or potassium hydroxide, aqueous definitely, and you get a Br minus. So this kinetic expression, this reaction mechanism which we are going to study next time, we are going to study in detail. What is the reaction? What is the kinetic expression? What is, next is how is the bond formed? What are the different aspects? This is the reaction mechanism which is showed. What are the silent features of SN2 mechanism? And what is the energy profile diagram? We are going to study everything in detail. And then also we are going to, so first we are going to study SN2 reaction mechanism, and then we are going to study SN1 reaction mechanism. So I'll stop my class here. Hope you are studying well and continue to study chemistry and all the subjects regularly, since you have got a lot of time now, and there are no practicals right now because of this pandemic. I wish you all a good health, and all of you try to take care of yourself and try to be careful with your health and try to be safe. So once again, thank you, and all of you please stay home and stay safe.